Hello, everyone. Welcome to another episode of Deep Dive Knowledge Talk. Greetings. Today, we delve into the convergence of manifolds, information geometry, and quantum computing in revolutionizing large language model training. We'll explore how these advanced concepts enhance parameter optimization, loss minimization, and overall efficiency, opening new avenues in natural language understanding and generation. How do the concepts of manifolds and information geometry contribute to our understanding of training large language models, particularly in how they relate to parameter optimization and loss minimization?
Manifolds and information geometry help us understand how large language models learn and improve over time. Imagine a manifold as a smooth surface, like the surface of a balloon. When you touch different points on the balloon, it feels flat around you, even though the entire balloon is curved. In training a language model, the data we feed into it can be thought of as scattered points on this balloon. Now, the model takes this scattered data and shapes it into a manifold, which represents the relationships within the data. This shaping is essential because different models can create different shapes or dimensions from the same data, like how different balloons can have different sizes and forms. The Fisher information matrix acts like a map that helps us understand how changes in one part of the model affect other parts. It's crucial when we want to optimize the model, which means finding the best settings, or parameters, to minimize errors during training, like trying to find the best way to drive a car to avoid bumps and get to a destination smoothly. However, once the model is set, we can only improve training to a certain point by using something called the natural gradient. Think of it as tuning a car's engine. You can make adjustments, but there are limits to how fast or efficient the car can get. This means that while we can make improvements, we might still hit a ceiling based on the model's design and how the data interacts with it. Overall, the interplay between the data, the model's shapes, and the way we minimize loss helps us understand the challenges and capabilities of training large language models.
In what ways does the introduction of quantum computing hold the potential to enhance the training process of large language models, particularly in relation to optimizing the parameter adjustments represented by gradients on these manifolds?
Quantum computing has the potential to significantly enhance the training process of large language models by optimizing how we adjust parameters represented by gradients on the manifolds of data. To understand this, think of training a large language model like navigating a complex maze where each twist and turn represents a decision about how to adjust the model's settings to minimize errors. In this scenario, traditional computing methods are like using a flashlight to illuminate one path at a time, trying to find the best route through trial and error. However, quantum computing can be seen as a powerful lantern that illuminates multiple paths simultaneously, allowing us to explore several possible adjustments to the model's parameters all at once. One of the key benefits of quantum computing is its ability to employ a special mathematical tool called the Fubini study metric tensor, which can create a quantum version of natural gradient descent. This is like having a super map that not only shows you the path, but also tells you which paths are faster or smoother to navigate based on the terrain of the manifold. Research has shown that, in simple cases, quantum approaches can outperform traditional methods significantly. This means that by harnessing the unique properties of quantum computing, we could find better and faster ways to adjust parameters in large language models, making the training process more efficient and effective. Overall, the introduction of quantum computing opens up exciting possibilities for optimizing the training of large language models, similar to how better tools and insights can help us navigate complex mazes more effectively.
What specific challenges in the current training methodologies for large language models might be addressed by applying quantum computing techniques, especially in relation to the scaling of model size and dataset complexity?
Applying quantum computing techniques to the training of large language models could address several specific challenges related to the scaling of model size and dataset complexity. One of the main challenges is the computational burden of optimizing the model parameters, as the size of the model and the dataset increases. Training large models often involves calculating the inverse of the information matrix, which can be quite difficult and time-consuming. Quantum computing can provide more efficient methods to handle these calculations, similar to how a powerful calculator can quickly solve complex equations that would take a long time to solve manually. Additionally, as datasets grow and become more complex, the traditional methods for training models can struggle with the sheer volume of data. Quantum computing can potentially process and analyze this data in parallel, much like having multiple people working on different sections of a big puzzle at the same time, leading to faster and more effective learning. Furthermore, the scaling laws observed in neural networks suggest that the relationship between the model size, dataset size, and loss can be quite intricate. Quantum techniques could help navigate this complexity more adeptly, allowing for better optimization strategies that adapt as the model and datasets increase in size. Overall, integrating quantum computing into training methodologies could lead to more efficient and scalable approaches, overcoming some of the limitations faced with traditional computing as we tackle larger and more complex language models.
How does the concept of the natural gradient differ from traditional gradient descent? And what advantages might quantum computing bring to optimizing this approach for training large language models?
The concept of the natural gradient differs from traditional gradient descent primarily in how it accounts for the geometry of the parameter space. Traditional gradient descent treats the space as flat, like a smooth table, where adjustments are made uniformly in all directions, regardless of how the model parameters actually relate to each other. In contrast, the natural gradient takes into account the curvature of the space, much like navigating a hilly landscape where some paths may be steeper and require different strategies to traverse efficiently. The natural gradient uses the Fisher information matrix to adjust the steps we take during the optimization process. It effectively reshapes the path we take to minimize the loss function by considering how changes in one parameter affect others, ensuring more efficient learning and potentially avoiding pitfalls like getting stuck in local minima. Quantum computing can enhance the optimization of the natural gradient approach by providing powerful tools to handle the complex computations involved, particularly with the Fubini study metric tensor. This tensor can create a quantum version of natural gradient descent. While calculating the inverse of this tensor directly in classical computing can be extremely challenging, quantum methods could make this process more efficient. In simple terms, think of it as using a sophisticated GPS that not only gives you directions but also adapts to the terrain, helping you find the best path through a difficult landscape. With quantum computing, we could navigate the parameter space of large language models more effectively, leading to better and faster training outcomes.
What role does the Fisher information matrix play in the training of large language models? And how might quantum computing enhance our ability to utilize this matrix in the optimization process?
The Fisher information matrix plays a crucial role in the training of large language models by providing insights into the geometry of the parameter space. It helps us understand how changes in model parameters affect the model's predictions. Essentially, it quantifies the amount of information that an observable random variable carries about the parameters of the model. In the context of optimization, this means that the Fisher information matrix can guide how to adjust the parameters effectively to minimize errors during training. When training a model using the natural gradient, which is derived from the Fisher information matrix, allows for a more informed and efficient path toward minimizing the loss function. This is because the natural gradient takes into account the curvature of the parameter space, ensuring that parameter updates are more aligned with the actual landscape of the loss function, rather than treating the space as flat. Quantum computing could enhance our ability to utilize the Fisher information matrix in several ways. One significant advantage is the potential to perform complex calculations more efficiently. The inverse of the Fisher information matrix is often difficult to compute in practice, but quantum techniques could streamline this process. For example, quantum algorithms could help approximate the inverse more effectively, even in high-dimensional spaces where classical methods struggle. Additionally, quantum computing can provide a framework for implementing the Fubini study metric tensor, which serves as a quantum analog to the Fisher information matrix. This could lead to new optimization strategies specifically designed for the unique properties of quantum systems, allowing for potentially faster convergence in training large language models. Overall, by leveraging quantum computing, we could harness the Fisher information matrix in a more powerful way, leading to more efficient training methodologies for large language models that are capable of handling the complexities of modern data sets.
Could you elaborate on the implications of using quantum algorithms for approximating the Fisher information matrix and its inverse in the context of large language model training, particularly regarding speed and accuracy compared to classical methods?
Using quantum algorithms to approximate the Fisher information matrix and its inverse can have significant implications for training large language models, particularly in terms of speed and accuracy, compared to classical methods. Calculating the inverse of the Fisher information matrix is often a complex and time-consuming task in traditional computing environments, especially as the model size and complexity increase. Classical methods, such as histogramming or kernel density estimation, can provide approximations, but they may not always be efficient or accurate in high-dimensional spaces. Quantum algorithms, on the other hand, have the potential to handle these calculations more effectively. Quantum computers can exploit phenomena like superposition and entanglement, allowing them to process multiple possibilities at once. This could lead to faster computation times when approximating the Fisher information matrix, enabling quicker adjustments during the training of language models. Moreover, quantum approaches might improve the accuracy of these approximations. The Fubini study metric tensor, which is a quantum analog to the Fisher information matrix, could allow for more precise modeling of the relationships between parameters in a quantum framework. This could lead to better informed updates to model parameters, resulting in more effective training and potentially better model performance. In simple terms, think of classical methods as trying to navigate a complex maze using a single path at a time, which can take a long time. In contrast, quantum methods are like having multiple paths illuminated simultaneously, enabling faster and more accurate navigation through the maze. In summary, integrating quantum algorithms into the process of approximating the Fisher information matrix could enhance both the speed and accuracy of training large language models, making the optimization process more efficient overall.
What are the potential limitations or challenges associated with implementing quantum computing in the training of large language models, especially considering the current state of quantum technology?
Implementing quantum computing in the training of large language models presents several potential limitations and challenges, especially given the current state of quantum technology. One significant challenge is the availability and maturity of quantum hardware. Quantum computers are still in the early stages of development, and many existing systems are not yet powerful enough to handle the complex computations required for training large language models effectively. Current quantum technologies often have limitations in terms of qubit coherence and error rates, which can make reliable calculations difficult. Another issue is the complexity of designing quantum algorithms that can be easily integrated with existing machine learning frameworks. While quantum algorithms offer promising advantages, they need to be tailored for specific tasks and require a deep understanding of both quantum mechanics and computational theory. This complexity can slow down the adoption of quantum computing in practical applications. Furthermore, there is a challenge of translating the mathematical frameworks used in classical machine learning, such as the Fisher information matrix, into quantum contexts. Although researchers are making progress in constructing quantum analogs to these concepts, the theoretical groundwork is still developing, which can lead to inconsistencies or difficulties in implementation. Finally, while quantum computing holds the potential for significant speed-ups in processing, the actual benefits in training large language models may vary depending on the specific tasks and models being used. It is essential to conduct thorough research and experimentation to determine where quantum computing will provide the most substantial advantages. In summary, while quantum computing offers exciting possibilities for enhancing the training of large language models, Various technical and theoretical challenges need to be addressed before these technologies can be fully realized and effectively utilized in practice.
How do you envision the integration of quantum computing, influencing the future landscape of machine learning and language model training, particularly in terms of innovation and potential breakthroughs?
The integration of quantum computing into machine learning and the training of language models has the potential to significantly influence the future landscape of these fields, particularly regarding innovation and breakthroughs. First, quantum computing could enable more efficient processing of complex data patterns. Unlike classical computers, which handle tasks sequentially, quantum computers can process multiple possibilities at once due to their unique property. This ability could lead to faster training cycles for large language models, allowing researchers and developers to experiment with more sophisticated architectures and larger datasets in less time. Second, the use of quantum algorithms could enhance optimization techniques, particularly in navigating complex parameter spaces. As mentioned, quantum analogues of traditional methods like natural gradient descent could provide more accurate and efficient updates to model parameters. This could result in improved model performance, especially in scenarios where traditional methods struggle, such as in high-dimensional spaces or when dealing with intricate relationships within the data. Additionally, quantum computing might open the door to novel approaches in model design and architecture. Quantum neural networks could lead to the development of entirely new types of learning algorithms that exploit quantum phenomena, leading to breakthroughs in areas such as natural language understanding or generation. Moreover, as quantum technology matures, it may facilitate new collaborations between fields like quantum physics and artificial intelligence, fostering interdisciplinary research that can propel innovations. Innovations. For instance, understanding quantum mechanics could inspire new algorithms or models that mimic quantum behavior, potentially revolutionizing how machines learn and adapt. In summary, the integration of quantum computing holds the promise of accelerating advancements in machine learning and language model training by enhancing efficiency, optimizing complex processes, enabling novel approaches, and fostering interdisciplinary innovation. As these technologies develop, we may witness groundbreaking changes in how machines understand and process language.
What steps or developments do you think are necessary in the realm of quantum computing and machine learning to fully realize the potential benefits for training large language models?
To fully realize the potential benefits of quantum computing for training large language models, several key steps and developments are necessary in both quantum technology and machine learning. 1. Advancement of quantum hardware. Continued improvements in quantum hardware are essential. This includes increasing the number of qubits, enhancing qubit coherence times, and reducing error rates. More robust quantum computers will be required to handle the complex computations involved in training large models effectively. 2. Development of quantum algorithms. There's a need for new quantum algorithms tailored specifically for machine learning tasks. While some algorithms already exist, creating efficient methods for approximating the Fisher information matrix and its inverse, as well as for optimizing training processes, will be crucial. 3. Integration with classical frameworks. Building interfaces and tools that allow for seamless integration between quantum computing and existing classical machine learning frameworks will facilitate adoption. This includes developing hybrid models that leverage both quantum and classical resources effectively. 4. Research on quantum neural networks. More research into quantum neural networks and their architectures is needed. Exploring how quantum concepts can be applied to enhance traditional neural networks, such as through variational circuits, could yield innovative breakthroughs in model training. 5. Exploration of quantum effects in learning. Investigating how quantum phenomena, like entanglement and superposition, can be harnessed for machine learning tasks will open new avenues for innovation. Understanding these effects could lead to novel learning algorithms that outperform classical counterparts. 6. Interdisciplinary collaboration. Encouraging collaboration between quantum physicists, computer scientists, and machine learning experts will foster the exchange of ideas and accelerate progress. This interdisciplinary approach can lead to a more comprehensive understanding of how quantum technologies can impact machine learning. 7. Addressing practical challenges. Developing solutions to practical challenges associated with quantum computing, such as error correction and qubit connectivity, will be necessary for ensuring that quantum systems are reliable for machine learning applications. By focusing on these areas, the integration of quantum computing into machine learning could lead to significant advancements in the training of large language models, paving the way for more powerful and efficient systems that can better understand and generate human language.
Thank you all for joining us today. I hope you found this discussion on the interplay between manifolds, information geometry, quantum computing, and large language models engaging and informative. To recap, we've explored how manifolds and information geometry provide a framework for understanding the complex optimization landscape of large language models, enabling more efficient parameter optimization and loss minimization. Quantum computing shows promise in further enhancing optimization techniques, leveraging its capabilities in complex calculations and parameter space navigation. By integrating quantum computing into model training, we can potentially unlock breakthroughs in natural language understanding and generation. However, it's important to acknowledge the challenges in quantum hardware, algorithm development, and practical implementation that need to be addressed to fully realize these benefits. We've delved into the potential advantages and challenges of this exciting intersection, and I encourage you to continue exploring these ideas and contributing to the advancement of this field. Thank you again for being here, and we look forward to future discussions on this topic.